So first, we'll start on metal additive 1.0. Metal additive, additive's been around for a very long time. It's not really a new technology in many cases. A lot of automotive manufacturers have been using it for some 20, 30 years at this point. But they've really been relegated to this 1.0 version, this sort of high cost, low throughput version of additive manufacturing. What we kind of like to liken it to is, today's metal, specifically laser powder metal 3D printers, are kind of like punch card computers back in the 70s. They have all this potential, but they require these specialized operators. They're very expensive. They require an entire room to be operated in. And you kind of take your design to somebody, and then maybe a week later you'll get a part back, rather than an instantaneous thing like we think about computers today. So what this really means for additive 1.0 in the application world is you have really high part costs. That's the only thing that's really able to support this specific, high capex machinery. So really high part costs, slow processing time. So really low volume, expensive parts that need the design freedom of additive manufacturing. That's what ends up being printed. So you see here an aerospace example, a medical example. Those are the kind of things that are being printed. Doesn't really fit very well in the automotive space because the automotive, at minimum, most manufacturers are producing hundreds of thousands of cars. So really those parts are not going to be able to be manufactured through these processes because of the cost and speed and throughput that is available today. So today, really, metal 3D printing, especially, fairly scratched the surface. It's been too industrial and expensive for this prototyping and tooling application. And then for volume production, it's not fast or cheap enough to produce it for 100,000 cars. So what we look at right now is thinking that additive is really at this inflection point where this 1.0 technology is mature, manufacturers understand it, use it to the best that they can. But there's this new generation of technology coming in, which takes the same principles and really turns that into a mass production machine that is more accessible to the everyday engineer. So that's what we're kind of calling additive manufacturing 2.0. And additive 2.0 is really driven by two main things. One is this idea of accessibility. So no longer do you have these specialized operators, these expensive equipment build-outs in order to utilize additive manufacturing. We're bringing it down and making it much more accessible, making it much more cost-effective and accessible to anyone, really, to be able to manufacture these parts. No longer requiring that highly specialized operator with specific training that is really dedicated to one or two machines. Additionally, on the other side, this idea of really high volume, high throughput manufacturing. So additive 2.0 is really focused on being able to take those designs and things that you might want to leverage with additive, but really being able to scale that up to a high volume, full-scale manufacturing environment like that in the automotive industry. So where Desktop Metal comes in, our mission is to make those industrial-grade 3D printing options accessible to all engineers, designers, and manufacturers. And what that really means is making our systems cost competitive. That's both for the capex of the equipment as well as for the end part cost, high speed and high throughput with exceptional quality for 3D printing. So what we have today is, a broad portfolio of products that really kind of are able to compete with traditional manufacturing at any scale. So starting at the bottom, we have our studio system there. That's kind of for those 1 to 100 prototyping use cases, really easy to use system that allows a design engineer to do a lot of iteration on parts, have functional prototyping out of metal parts. Then in this midsection, what you're seeing is the shop system on the left and the P1 system on the right. Those two are really systems designed for hundreds to thousands of parts. So really, something that you would otherwise be doing some sort of extrusion or investment casting in order to produce those parts. That is where the shop and the P1 production system fit in. And then as you scale up to this high volume production, the shop and P1 kind of fill into that mid-volume production as well, depending on the part size. But the high volume production, that's our P50 production system, is really where you're talking about getting cost competitive parts versus traditional casting, metal injection molding, press and sinter, all those kind of technologies. You're getting cost competitive parts via 3D printing with that system. And that's the one that really has the throughput to keep up with the manufacturing lines of today at scale, to have a part printed on the production system in every car that's coming across the line. So today we're going to be focused mostly on this binder jetting technology, especially for the end use section, but we'll talk about all these products today. So how does this technology actually work? So behind all of this, these great applications and great ideas, what's actually happening to make this end use metal part that you have are able to hold in your hand and actually is metal? So all of our printing systems are built around the chemistry and powder supply of metal injection molding. Now, metal injection molding is something as an automotive manufacturer, I imagine many people are pretty familiar with. There's a lot of metal injection molded components in cars, as well as press and sintered, similar sort of technology. But basically, metal injection molding is a powder metallurgy process. So the benefits of it are that you can have really complex shapes and mass produce these parts from relatively inexpensive metal powders. Very well-known technology, like I said, it's in a lot of products, especially automobiles today. So there's widely accepted and validated standards such as ASTM and ISO and PIF standards around these. The other nice thing about metal injection molding, one of the reasons why we chose it to base our systems on, is it's a broad range of compatible materials. So you have your stainless steels, alloy steels, as well as a lot of other specialty materials that can be produced via this metal injection molding process that then could be transferred over to the 3D printing process that mimics the same approach. So these metal injection molding powders, the MIM process really gives you very good mechanical properties, metallurgical properties. So what you're looking at here is sort of a graph showing the ultimate strength and elongation of break. And you can see MIM is not quite at the level of a wrought material, but really it is right there and again, widely used and accepted as a manufacturing method for metal parts. And you can see it's even better than press and sinter, which again, a lot of automotive components today are press and sintered as well. So how MIM works, what it does is it takes this metal powder and mixes it with this polymer binder into this feedstock. It's this combined powder mixture. And then it uses basically the same process as a plastic injection molding to create these shapes, create the shape of the part. Now, obviously that requires tooling, right? So you're creating this tooling to have your design, putting that in, putting the metal powder into that tooling, creating the shape. And then what that does is actually forms what's called a green part that then moves into this debind and sinter phase to then bring it down to a final full metal part, fuse those particles together, get rid of any of that polymer binder, and you have a full metal part just like any other. So with MIM-based 3D printing, we're taking that process and applying it to our system. So the studio system uses rods that are pre-mixed of that metal powder and that wax polymer binder. That creates the shape via this printer, which is basically similar to an FDM process where it extrudes through a nozzle to create your shape. That creation of the shape happens, and then we actually do the debind step within the furnace. It's a thermal debind. Thermally debind the part and sinter the part down to a full metal part right in the furnace. So mimicking the same thing, using the same materials, ending up with a part that is widely similar to what you would get at a metal injection molding process. Now, the binder jetting technology is even more similar, where it actually uses the metal powders that are the same as the metal injection molding powders, uses those and actually prints those through a powder bed process and prints those parts within a bed of the printer. So rather than extrusion-based, it's a layer-based system. So that gives you a lot more economies of scale when it comes to scaling up these parts, which is why the shop and production system are so cost effective. Then those same parts, same deal, put into the furnace, thermally debound and sintered in the furnace, and you have your full metal parts at the end of the day. So the studio system, as we said, low volume applications, functional prototyping, jigs and fixtures, rapid tooling. It's safe for the office, really easy to use. You just come plug it in. Within a couple days, you can get your parts ready to go and being used in real applications. Also, a wide variety of materials available here. We have a few currently developed and then plenty more in the pipeline. Shop system and then the production system. Shop system is this binder jetting technology, which is sort of batch productions of these end use parts. And then being able to go through and do sort of hundreds of parts a day with this flexibility of having a build box to work with. We'll talk a little bit more about what that flexibility gives you. but that just gives you an idea of the shop system. And the production system is basically this, just at a bigger scale, high throughput, really ready. You can see my virtual background here is a couple production systems, large scale 3D printing. So now we'll get into the meat of it, talk a little bit about part examples and things like that. Automotive, there's plenty of metal parts in an automobile, in the automotive industry today. Not all of them are the right fit to turn into a 3D printed part, but plenty of them, especially anything that is in this metal injection molded or press and sintered world, is a great example to use, or a great application for metal 3D printing. But before we dig in fully, I'll talk a little bit about our customers. So we have a broad range of customers across a variety of industries. Plenty of logos that I'm sure you'll recognize up here, but also a few that you won't. And that's really important for us, tying back to that accessibility idea, where yes, the Fords and the BMWs of the world are customers of ours, but also these smaller manufacturers that are maybe tier 2, tier 3 manufacturers that maybe wouldn't have been able to afford a laser-based 3D system or really justify that system, are able to be purchasing and using metal 3D printing with our system. So that's really a big benefit of us. Specifically in the automotive space, a lot of the big guys are, using this technology actively, both from a, let's understand how this works so we can figure out how we can use it in future product designs, all the way to, using it today to produce parts that are helping their manufacturing floors or producing parts for end use. So back to that sort of product life cycle, we'll go through the prototyping side first of how 3D printing, specifically Studio System, that's kind of its sweet spot there, can help with the prototyping side for the automotive industry. So here's a part example. It's a transmission shift fork. So it's a piece found deep in the transmission of a car. So basically, this is normally, at scale would be cast, right? It would be cast in high volumes. But when either replacement parts you need or when you're trying to really optimize that design, this transmission shift fork is something that would not be easy to produce any other way, almost impossible to produce any other way because some of the geometry on there. So basically, this part is able to be printed on the Studio System for $88 versus some sort of quick turn casting or something like that that would require both more time and cost. This is also something that you put your part in on a Monday. By Friday, that part's out. Rather than waiting to send it off to a foundry or to some sort of casting house to try and get a quick turn sample back. Another part example here is connecting rod. So obviously an integral part to the engine here. Traditionally this would be forged followed by a bunch of machining operations. By being able to print this part and machining those critical dimensions reduces the amount of machining time that needs to be done on the part and frees up the machine shop for other work. So that would also impact your cost savings at the end of the day. So what we're looking at here is a much lower part cost and a significant savings. And really, this is, again, to talk to the prototyping side of things, maybe it's not something on the Studio System you're going to produce connecting rods that are going to go for every car that you're manufacturing. But as you're trying to optimize that design and try and test out which design is best, that's where the Studio System really comes in and works great with this part. The shock absorber piston is a great example, again, of that design iteration, right? So you can imagine these shock absorber pistons, they have these internal channels. Maybe you're trying to do something that doesn't have a round hole, maybe all these different sort of features to it. Traditionally, these parts are going to have to be made through some sort of casting because of the way that those internal channels are routed. With the shock absorber piston you see here, what the engineers were able to do is really print 5 or 6 different designs all at once. Again, print them on Monday, by Friday you have them out, by Thursday, Friday you have them out. And then they're able to simultaneously test all these different designs. Going back to that time to market challenge that we're talking about here with the automotive industry, this is a great benefit where you don't have to lock in on one design, go send that design out and have it manufactured. You can actually print multiple designs in parallel and really quickly iterate on your processes to better understand your parts and make better optimized parts at the end. Maybe eventually this is going to be metal injection molded or something like that. But for the prototyping use case, great example for the Studio System with those shock absorber pistons. Now this is another example. A lot of things with additive and even with additive 1.0, as people have produced parts, generative design is a big thing that people are are excited about. So this is an example of the piston head made with generative design. So you can see all that lightweighting and stuff down at the bottom to really cut the material out that isn't really needed in order to have enough strength for the part. So with the Studio system, these designs can be prototyped and tested, speeding up that product development and really test it out to understand if this is something that makes sense to move into mass production. So we'll touch quickly on the aftermarket use case as well. So, as we said, aftermarket spare parts support for automobiles is a huge, huge part of any manufacturer's, sort of portfolio of what they do. Aftermarket parts are a great use for metal 3D printing, because really what you're looking at is parts that are not often, they don't need any minimum lot size in order to make these parts. Say if you had a part that was 30, 40 years old, would have to get cast, you would need at least a good amount of orders or support for that part in order to justify the minimum order quantity from a foundry. So that's exactly what we're talking about here with this thermostat housing. So this is a thermostat housing for a vintage Mercedes engine. This is something that was back in the day was cast. Obviously, the tooling and all of the molds for this part are, no longer able to be found anywhere. And this geometry, it's something it's a little too complex for machining. Maybe you could get it, but those internal channels aren't easy. There's a bunch of, features as where those holes go in that wouldn't be something that's too easy to machine. So you're really looking at some sort of low volume casting process, which doesn't really justify low volume. And these are parts, there's only a handful of these cars out in the world today. So these are parts that are needed on a very low volume. So what you're able to do with 3D printing is take the original part, model it up, and then turn that into you can print that part whenever you want, as soon as you get an order in, right? So when Mercedes has a new order for this particular part, they can just print it and then send it out to the customer, and they're good to go. So really being able to quickly reproduce, have that just-in-time inventory, and not have to pay that fixed cost to get the foundry spun up is really the benefit that we're looking at here with the aftermarket MRO use case for 3D printing. All right, so now we're going to get into the mass production side of things. Plenty of interesting applications, use cases here. Kind of broken into two parts to better split it up. First, we're going to talk about mass production being supported by additive via manufacturing tooling, so being able to produce manufacturing tooling for your manufacturing floor. And then second, we'll talk and dig into a bunch of end-use part applications at a mass production scale with the shop and production systems. So manufacturing tooling, what we're looking at here is really a lot of jigs and fixtures, end effectors, things like that, QA devices, things of that nature that are able to really be otherwise maybe would be made out of machine, but you really don't want to clog up your machine lead time, your machine shop with these kind of parts. You want to keep them to customer parts or critical parts, something like that. Also, with 3D printing, you get the design freedom, so you're really able to make some custom components that otherwise wouldn't make sense to manufacture some other way. Additionally, a lot of interesting examples here for tooling as far as molds, mold inserts, things like that, as well as some sheet metal tooling, extrusion dies, things like that. So this is our first customer case study we're actually going to talk about today. It's a company called Egar Tool Die. They're based out in Canada. They are a automotive stamping and welding supplier. So they've been doing this for 40 years. They have 200 employees across 2 different plants. So well established in the industry up in Canada. They have this interesting approach to additive manufacturing. They're very forward thinking with it. The way that they look at additive projects, if it meets 2 out of these 3 criteria, they'll fund the project and greenlight it to be printed. So one dimension is cost. So is it cheaper to actually print the part than it is to make it in-house or buy it, whether it's their internal machine shop or if they have to outsource it to some sort of foundry or something like that. Obviously, that's a pretty easy, clear win one way or the other. Speed. Can we get it printed faster than we can get somebody else to make it or even make it in our own building? Like a lot of manufacturers today, machine shops are sort of overworked and understaffed. So being able to print something and not have to take up that machinist time oftentimes turns out to be quicker than even a relatively simple part getting machined. because it has to get put into the back of the queue and work its way up through the machine shop. And then lastly, the last dimensions they look at it on is weight. So specifically on their end-of-arm tooling applications and their welding fixtures, can we reduce the wear on those machines, increase the cycle time, or reduce the cycle time by reducing the weight of that end-of-arm tooling? So it's another interesting vector that maybe not everybody thinks about right off the bat. So this is an example of that end-of-arm tooling like we were just talking about. So with the Studio system, what they were able to do is actually print this tooling in 17.4 steel. So that top part you see there is the original design they had that was made out of nylon material with some steel inserts. So that nylon material with steel inserts, you can see it's pretty bulky. And the reason why it's so bulky is that it needs that strength in order to be used for the application. Additionally, because it's so large and it has the steel inserts in it anyway, that part actually ends up being heavier than the all metal part you can see below. So what they were able to do is they were able to knock that lighter dimension as well as the cheaper dimension by producing this part via metal 3D printing. Another end-of-arm tooling example, similarly, they were able to cut these cavities out of it to reduce that weight on their end-of-arm tooling. And then at the end of the day, what's interesting about additive is every piece of material you remove, you actually are reducing costs because you're using less material. Versus machining, every additional cut you put into it takes your machinist more time, so you're increasing costs on the part. So that's why this end-of-arm tooling use case is really a great one, because when you really want to reduce that weight, additive gets more cost-effective the more weight you take out versus machining, which is the other way. Additionally, stamping dies. So this is a great example of something for the automotive industry. Obviously, a lot of stamping goes on in the automotive industry. Metal 3D printing can really easily support that, right? If you have a relatively small run of something and you need that die made, oftentimes it's probably going to be easier to print that die than have, especially some of these complex geometries, than have it machined. So you can see here, these are actually printed in H13, so a great material for stamping. They actually TIG welded these sections together onto the to sort of a blank so they could put it into the machine. And what they did here is, they had a printed part. They were able to just quickly quickly machine the surface just to give it an even finish. And at the end of the day, you're talking about a much quicker part and a much more cost-effective part for them. Additionally, here's a great example. Again, touching on that generative design sort of use case for topology optimization. So what this is a timing belt pulley on an engine or on a servo that they have. Basically, this is a heavy part. You can see it's 3 or 4 parts that are all bolted together. What they wanted to do is make this a much lighter part so they could move that servo faster and go back and forth quicker. Additionally, this is a part that when they have to replace it, it's a big part, big block of material. They got to machine a lot out of it in order to get to the final state. So with additive, they were able to actually take this and print this part in this new optimized design that fits all of their strength requirements. The software they use to do this topology optimization made sure that fits all the strength requirements that are needed, is printed both quicker as well as in a lighter fashion than the original component. So big savings for them there. Last thing they'll talk about here is these copper electrodes. So like I said, they do the stamping side of things. They also do a lot of welding. So what these do is actually hold electrodes in position during some resistive nut welding. Copper obviously is a great material for this because of its conductivity. But really what we're looking at here is an interesting thing as well of adding conformal cooling to a part. So this is something that machining-wise you couldn't really do. This part actually has, you can see those holes on the top, channels that go through the part that they can pump water through to keep that part cool. This reduces their cycle time and allows them to, just push more parts through the same manufacturing process. And that's something that really only can be done via additive. Otherwise you'd be machining in holes and trying to plug holes, and it really wouldn't be cost effective to do any other way to put those conformal cooling channels in. So really, at the end of the day, what Metal 3D printing has done for Egar is turn their manufacturing operation, made it far more efficient. That lightweighting of the tooling, the conformal cooling of the welding fixtures, those stamping dies, and really just being able to either on the one side of things make things lighter so their machinery can run quicker, or on the other side of things produce things quicker or cheaper than they could in-house. So really big benefits for Egar there. Another manufacturer that we, as one of our customers, is Eaton. Eaton, you may be familiar with them. They have a broad range of different groups underneath the Eaton umbrella. Some of the lights in my house are produced by Eaton. But really, the first group that adopted this metal additive technology from Desktop Metal was their vehicle group. So this is their automotive and truck business. So really what they were looking to do here is try out this metal additive manufacturing. They had some polymer 3D printers already in use. And those polymer 3D printers, they've been able to find use cases for them and plenty of things like that, but they really wanted a metal printer in order to support a lot of the activities on their manufacturing floor. So that's where they ended up with the studio system. So what they were looking to do with Metal AM, obviously, as we talked about, produce prototypes to reduce the product development cycles, bring that time to market, and that's a big thing for a lot of customers. Second is tooling, fixtures, and other sort of devices like that, trying to produce those safety devices quicker in order to, again, accelerate time to market. It's a big constraint for them. And then the other side of things on the MRO side, specifically on their manufacturing floor, plenty of machinery that they have is quite old, and some of them even the manufacturers aren't around anymore for. So with that, they're looking to reproduce these MRO components quicker and not have to go try and source some part from a 50-year-old machine from the supplier. And then the kind of added benefit to all of this is gives them this design freedom and ability to consolidate assemblies all together and reduce the amount of parts that they have to support. So here's a bunch of examples. We'll talk through one of each of these use cases, but this is a bunch of examples of replacement parts and tooling components. So like I said, most of these parts are for machinery that is, not even around anymore if they're replacement parts. And then the tooling components are custom pieces, to try and, like this assembly bearing press tool, to try and fit a new design into an existing machine. So all of these things are great examples that Eaton has printed. You can see on the chart a little bit, the cost savings that they're seeing. So they're seeing, 60, 70, 80%, sometimes even 90% cost savings versus doing this either outsourced or within their internal machine shop. So this is one great example. So you can see a pretty significant reduction in cost here. What this is a component to sort of guide a chain along one of their furnaces. Traditionally, they machine it, they'd heat treat it. This actually turned out to be a lower cost to produce versus buying from the external vendor who normally does their machining. Quicker lead time, they just were able to 3D scan the part, rebuild the model, and get it printing, all within a week. So you'll see here some photos of it printed, gone through and debound and sintered, and then you'll see it actually in action there on that, doing that chain guide. And that's at the end of the day, the real use for this part. Something that is not a super structural part, it definitely has wear, so it needs to be metal, but great example of being used for metal 3D printing. Additionally, we have testing fixtures and gripping components. So again, similar to Egar, they're looking at this as a great example for grippers and end of arm tooling. Again, significant cost savings in a lot of these examples, as well as some of that weight savings that Egar was looking at as well. One example I'll talk about here are these chamfer chuck jaws. This is one that uses that topology optimization. And again, like we said, this is something unique to additive where end of arm tooling is something you want to keep as light as possible. Typically when you're machining it, the more material you take out, the more expensive the part is because it takes longer to machine. With additive, you're only using the material that is in the part. So you're actually creating the more material you're able to take out, the more cost effective the part is. So you can see a significant cost savings here, and you will compare it here to the original on the left. And you can see they took a lot of material out of that made it a lot lighter, as well as actually, more effective at its job. Much improved design for Eaton there. So business impact to them, really one of the interesting things is it's challenged them to think differently when addressing a problem or finding a problem to fix, rather than going and calling the supplier and trying to fight through to get the right aftermarket part that the supplier at that point is then going to have to figure out how to produce if there's no molds or something for it. They're able to address these issues quicker in-house and just get it done and keep the manufacturing line up. Increased equipment uptime is huge for Eaton, and a big reason why they're looking at these systems. And then again, reducing those costs on the manufacturing floor. One interesting point on Eaton is they actually expanded across many of those other groups. So there's 4 systems sort of spread out across the world today at different locations doing these same sort of applications. And they're looking at the binder jetting technology, which we'll touch on a little bit, for production level parts. One more case study here. Innovative Plastics are an injection molding firm based out of Alabama. So Innovative Plastics, a lot of different industries they cover. One of them is automotive, but boating, medical equipment, consumer products, a lot of different stuff. And really what they're looking to do is reduce the time to manufacture these critical molding components. So as many people know, a lot of plastic components in cars are injection molded. It's kind of the most cost-effective solution in a lot of ways. So what they're able to do is use metal 3D printing to really reduce the amount of time and give them a little bit more freedom when it comes to producing new molds for customers. So, obviously the injection molding kind of process, many people might be familiar with, but really, you're looking at creating a mold that's going to stand up to a lot of use. So many, hundreds of thousands or even millions of shots of parts coming out of this mold. And it kind of has to do that on a repeated basis. So cycle time is very important, as well as, the lifetime and the wear on a part. So that's why, metal is used for this, and specifically metals like H13 tool steel, great material to use for injection molding applications. So designing the mold, most of them are produced with CNC or EDM processes today. And really what that means is that when you have a part that, is designed by the designer and you have that ready to go, it's going to take some specialized resources to actually turn that part into a CAM file or whatever it needs in order to really get it set up to be machined. And then you're, again, running into machine shop bottlenecks, running into, don't have enough machinists on staff. That's where really a lot of people are hitting the bottlenecks with mold design, and where 3D printing can come in. So what 3D printing enables you to do is kind of print those near net shaped parts, print those parts pretty much close to where it needs to be. If there's some specific, tolerance that needs to be really, really tight, you can do a quick machining pass that is a, 2-second operation. That's a quick pass in order to touch up that final dimension. But the hard part, the majority of the time you're going to spend programming a machine is programming a CAM into the machine is already taken care of with the additive manufacturing. Additionally, with AM, you have these benefits, like we talked about with those conformal cooling channels and some of the welding fixtures. Conformal cooling channels with molds really reduces that cycle time and allows them to push more parts through this process and making their manufacturing line more efficient. So you can see here they printed the core and the cavity, 11 hours to print the core, 30 hours to print the cavity, and then they flipped it in and sintered it. So at the end of the day, it's about 6 days to the part. Now, when you factor that in versus, you have your design ready, factor that in versus sending it to the machine shop, having somebody get ready to put it in the CAM, machine that part out, touch up any final pieces. If they need to do an EDM process, additionally, that's going to be added time. At the end of the day, this 6-day process is oftentimes a lot quicker than the process that is existing for their machining. And the big thing is all of that was done with no operator, right? So they go in, they upload the file, click print. All you have to do is move it from the printer to the furnace, and that's the only hands-on parts that you're really working with. Versus machining, where somebody's always pretty much with the machine, making sure that it's doing the right thing, producing those parts. So and the other thing that's important to note is with our systems, we're really designed for batch processing. So it's not just print one one part in the 6-day time frame, you can print, depending on the part size, in this example, probably 4 or 6 parts, and get those all set and ready to go in that same 6-day time frame. So post-processing, so they did a little bit of post-processing on this part. And then at the end of the day, this mold, is in action. You can kind of see down on the left side, the plastic parts that are getting shot through that mold. And really, and what this particular part is an exhaust cover cap for a boat motor. So really far quicker process for them to get that mold created, reducing the cost for them. So brings the original cost to produce that mold in the $10,000 to $12,000 range. The 3D printed mold, even including the post-processing and CNC time, brought that down to about $6,000 to $8,000. So, roughly 30, 40% savings from metal 3D printing. And the business impact, so with the conformal cooling channels, they were able to shave 3 to 5 seconds off that cycle time. So that, puts 20% improvement in the speed that they're able to produce these parts. So they can produce 20% more parts per day. So this really kind of has impacts, not just at the production of the mold stage, but down the line of, if they're producing hundreds of thousands of these and they can squeeze an extra 20% per day out, that's going to drastically reduce the amount of, the cost that they're associating with these particular products. Especially the other interesting thing here is that they're reducing their dependence on their other existing tooling, especially EDM, for recreating these molds. So giving them another option, another tool in their bag in order to make these parts. All right, so we have about 15 minutes left, and we're going to talk all that time about end-use parts. This is, I think, what a lot of people are very excited about with additive manufacturing, specifically the binder jet systems. So just talk a little bit about why binder jetting is the solution for producing end-use parts versus some laser-based systems or things like that. Really, binder jetting works for mass production because it's a high throughput process, right? It uses this area-wide raster-based 3D printing rather than a laser-based system, which doesn't, which has a specific spot that it's printing on at any time, or an extrusion system that only extrudes in one spot at any given time. This actually uses the entire print bed, just like an inkjet printer, and prints all at once. So that page of powder gets printed very quickly. Additionally, those low-cost inputs that we talked about from the metal injection supply chain, that really allows you to have cost-effective parts coming out of the furnace. At the laser-based systems, a lot of them have very specific materials that you need to use in order to have the right part properties. We are able to make parts with relatively inexpensive materials that you would still be, that you'd be paying for to make your parts any other way. Additionally, these material properties are isotropic because we do that final sintering phase. Those parts consolidate down and become pretty much isotropic. And this is very easy to scale out to large build box sizes and large parts with very low waste, because anything that is not actually printed as a part is a recyclable powder. Unlike, again, the laser-based systems, you're very restricted as far as what can get input into that system to produce a part. Binder jetting has a very low waste process, and you can reuse almost all of the materials. So you can see here, example of that layer-based or area-wide printing system. So I touched on this a little bit earlier, but really what that enables you to do is you're building these boxes of parts. And in 8 hours, you're going to build a box of parts, regardless of what's in it, because it prints a layer every second, or whatever depending on the settings that you have. So being able to produce a box of parts in a certain amount of time frame, so for example, 8 hours for these boxes you see here, being able to produce a box of parts in that time frame allows you to put anything in that box. So you can say, I'm going to have one of every part, or one of a bunch of different customers' parts put into that box all at once, and you'll get a bunch of different parts out. You can then say, okay, these 3 parts are moving into a pilot phase, so let's batch produce those parts in the tens per build, and you can do, as you can see here, tens of 3 different parts, right? And then when you're ready to actually go to mass production, even with the shop system, the smaller of the systems, you can produce hundreds of thousands of parts per day with this system, all the same part packed into really densely into this one build box. So really valuable, the flexibility of manufacturing you have. You're not paying for tooling, so you're just able to kind of, explore and change the designs as you need to. So let's take a look and compare this to some of the common traditional manufacturing methods. So the three we'll kind of look at is machining, casting, and powder metal. So the challenge that you're running into here is, long lead times due to the fact that all of these processes pretty much require some sort of tooling or setup time. Additionally, there's a lot of NRE, non-recurring costs associated with them. With the casting and powder metal, you're talking about the tooling getting produced. On the machining side, you're talking about the programming time and the machinist time. Additionally, these are very industrial processes. When we talk about accessibility, I don't think many people would consider casting as an accessible process. And then custom machining and post-processing and all of these other pieces add a lot of lead time and part costs, especially when you have to go through multiple steps of the process. So what this ends up meaning is you're talking about months to bring a production line up. You're stuck with your designs for longer, and then you're sacrificing the flexibility and the ability to optimize these designs to make it easier to manufacture. And specifically on the powder metal side, you're talking about really high tens, hundreds of thousands or more quantities in order to justify the high tooling cost that starts out there. So from a timeline perspective, what does it look like for this? So machining, it sort of depends. If you get it in as a rush job, it's in the front of the queue, you're going to pay for it, but you can certainly get things done quicker. But typically what we see from customers in this industry is you're talking 1 to 2 months for, I have a part ready to, design ready to be made, and they submit it to the machine shop. By the time the machinist is able to produce that part, especially if there's, multiples of that part that need to get made, by the time they set it up in the cam, produce it, check it, do all those steps of the process, you're talking 1 to 2 months to get a part back. Casting, obviously, even more, right? They have to actually produce the tooling and then start casting. So, prep is quite a few weeks, 14 weeks or so. And then actually production, is a process. There's multiple steps in creating this cast part. Metal injection molding, even more. You're talking 5 months. That tooling takes a lot of time to get put together. The build prep takes a lot of time. They're really setting up a manufacturing line for each of these processes, for each of these parts. So that's at least a 5-month lead time for a lot of metal injection molded parts. And what you're looking at, if the design changes, these processes pretty much have to start all over. Hopefully, machining, they can maybe make some tweaks, but they'll probably have to kind of start from scratch again on the CAM programming. Casting and MIM, hopefully you can make some changes to the molds, but likely if it's a significant design change, you're going to throw that mold out and start all over again. So with binder jetting, what you're able to do is do all these processes, same thing with these produce the same parts that these processes are producing in that 1 to 2 week time frame. You're able to upload a file, click print, have it come out of the printer, a week or so later. Even if you start adding on the post-processing times, you're still significantly quicker than, a lot of these other processes. And when the design changes, you just upload a new file and you get it off in that same time frame. You don't have to worry about changing any tooling, changing any programming in order to get that part correct. So what that really means is, binder jetting allows you to do this mass production without tooling. It allows you to create parts like this without investing any of the money in tooling, give you that design freedom, give you that flexibility in manufacturing. So first on end use parts, we'll talk about sort of mid-volume production. So I'll call this like the shop system, the shop system sort of sweet spot, or maybe a little bit, if you're flexible runs in sort of a production system. So really what we're talking about is pilot runs and then this ability to mass customize. So on the pilot run side, this is an example of a taper lock coupling for a custom motorcycle, right? So relatively low volumes, they're producing a few of these to start, and then, scaling up manufacturing to, a few hundred or a few thousand. And really this part, it's not would not be an easy part to manufacture via any other method. So really what they're able to do via the shop system is reduce the lead time to create this part, scale it up as quickly as they need to, and then give them this flexibility of design freedom of, I'm going to add all these features into this one part rather than try and split it out and put these different features into different parts. This is the gear shift knob. So this is an example actually of mass customization, right? So if you're talking about producing, say a limited series of cars, say 5,000 cars for a certain limited run, what you can actually do is say, okay, for that 5,000, we're going to do one of those parts. This gear shift knob is going to be custom, right? It can be custom just for that specific model, or it can be custom down to each individual can select their design, and it doesn't cost anything to change the design when you're making it. So really what this is able to do is change that design, make on-demand manufacturing of custom components really cost effective. You're talking about a $50 part cost here, which, short of, a full-scale casting or metal injection molding production, you're not really going to be able to produce that at a better, more effective cost. And actually on this, I'll say that the throughput on this, you're talking about almost 200 of these per week. So there's really the ability to produce a significant amount of these parts. Another example here is this water wheel. It's a BMW part. This is obviously a piece of the cooling system on an engine. What they had done here was initially made, the original design was several plastic parts. Then they redesigned it for printing on a laser-based system. But that laser-based system was way too expensive for any sort of production, even in a low volume of street cars. So what they're able to do is come through with the production system and actually unlock this higher throughput at a cost-competitive price. This is a $13 part that they can actually produce 167,000 of per year. So that really enables them to take this optimized design, this better design, and produce it at a scale that supports their manufacturing operations. Another great example here is a company called Turner Motorsport. They're out of Massachusetts here, and they're a leading BMW race team and tuner in North America. So you can see here a couple of their IMSA competition cars running around the track. But basically what they were able to do with metal 3D printing is really a couple of interesting applications. So one project the project they started coming to metal 3D printing with was they're working on this engine swap, taking a 2001 BMW M3, which had a straight six engine, and putting in a newer V8 into it, kind of the holy grail of BMW engines into this older M3. Now, obviously, dropping an engine that has two more cylinders and is actually probably twice the size of the original engine, it's going to come with some challenges. So what they found was one of the things they needed to produce is this engine mount, right? The engine mounts aren't going to match up perfectly. So they need to take the original engine mounting points and figure out how they're going to connect that to the new motor. And in doing so, they have to do that while not interfering with any of the rest of the components that are squeezed into that engine bay. So what they did is they came to us and actually used one of our softwares called Live Parts to generatively design this engine mount for this car. So you can actually see here the part being grown and all these forces being taken into account, all the area that they can have parts versus can't have parts being taken into account, and it's all produced via the software. So what they ended up with was this design that they were able to rapidly iterate on, right? So you can see here, there's, some markings on the part that say, hey, this isn't going to fit, with the steering rack in there. We need to cut out this section. So they're able to go back to the software, iterate on the design, and end up producing this final two-piece design. This was a part that was so big that it wasn't able to be produced in one piece on our system. And so what we ended up doing was welding the pieces together, and you can see that weld, beautiful weld, from a race team there, but welded perfectly and is currently installed on the car today. So you can see really, really tight tolerances they had to fit that part in, but with metal 3D printing, they were able to have that geometric freedom while still being able to produce a part in a cost-effective manner. Additionally, once they have this system, they're able to produce all these other custom parts in this low mid-volume range. So like this knock sensor housing is something that they needed to make custom for this engine swap. So they were able to produce this with the metal 3D printing system. Might have been definitely something that would be machinable, but it was actually easier for them just to, rather than take up their machinist time with it, just print it. They have the printer, just print it, and they're good to go. So really the business impact for them, they were able to prototype and iterate on those designs in parallel, which gave them quicker time to the actual part. And then they're able to scale that up into an actual, pilot run or production line as they're needed. And the big thing here is, they're a relatively small team, but this is really a breakthrough innovation for them in the hands of such a small team. All right, so then now we'll talk, this mass production scale, what this looks like for additive manufacturing and how cost competitive you can be versus traditional manufacturing. So here's an example, a lock plug, obviously, a part in many cars, some sort of locking mechanism. This is something that, can be produced on the shop system for $5 a part, and that gets even cheaper once you go up to the production system. So, you can produce 10,000 of these, almost 10,000 of these parts per week on the shop system, and then change that design or stop that design as soon as you need it. So really flexible manufacturing at a cost-effective scale. Additionally, this fuel swirl, so I actually have this part here, I'll show it. So this is a fuel swirler, a little closer, for diesel fuel. So this is something that, mixes the fuel together to have a better burn in the engine. So this is a part that on the shop system can be produced for $5 a part, and almost 3,000 of these parts per week. So that's at a scale that we're talking about is really supporting a full-scale manufacturing operation for these. And then obviously the best, added bonus is the fact that you have the complexity of this part, those intricate fins and this sort of these internal features all come for free, basically, right? You're not paying more money, more time to have a machinist cut those out, or some of these parts might not even be able to be produced via injection molding or metal injection molding or casting. Another example here, also got this one. This is a little star shifter. So this is a part of a motorcycle transmission. So you can see pretty complex, probably could be metal injection molded, but definitely, going to require some tooling in order to do that. So basically, they were able to produce this part, on the shop system relatively cost effectively. And the big thing for this customer was this part can actually benefit from being slightly changed based on the application that it's used in. So even though it's the same transmission that they're going to use in multiple different motorcycles, actually this part, changing that design of the part, tweaking that design a little bit, can provide a better end product. So what they're able to do is tweak that design, again, for free, essentially, and produce that part slightly differently for a different bike, and they can produce 1,500 of these a week. So if they have 3 manufacturing lines going, they can produce 3 different designs, all in 1,500 of those, split across those 3 designs per week. Another example here is this clutch plate, again, connecting an electric motor to a crankshaft to start a motorcycle. So this is something you can see that has those kind of curved edges there. Not something that would be very easy to machine. So what they were able to do with this part is actually print the complex part of it and just do a quick touch up with a CNC on a specific part that needs a critical dimension. So that at the end of the day means their machinist just needs to touch up, the 200 of these parts that come out each week, rather than spending, hours and hours machining each one of these out of the material. And at the end of the day, they're looking at a $60 cost per part, and it's a pretty large part as well. So another one we have here is a seatbelt pulley. This is something that typically would have been press and sintered. So, definitely a part, nothing, crazy from a geometry's perspective. There's a little bit of complexity in there that makes it, tough to press and sinter, but it's certainly doable. But really what printing on the production system does, able to make that part cost competitive with that manufacturing process. So this is a part that on the production system costs just over $1 per part. And that with this, especially with the advanced sliders that are going to be needed for the press and sinter, is actually going to be a more cost competitive part. And you can print almost 2 million of these parts per year with just one of these production systems. Another example here is this parking chip bracket. This would take a couple operations to produce via, metal injection molding or press and sinter. But certainly, again, something that people have been doing. Really what the production system does reduces that need for that complex tooling, and it actually reduces, at the end of the day, the part costs. And with this particular part, they were able to consolidate a couple pieces of the assembly into a single part. So at the end of the day, this is less than a $5 part, and you can produce almost 500,000 of these, or over 500,000 of these per year on one of the production systems. Another part here is power steering joint. So this is electric power steering motor and steering shaft come together. This is the joint that holds those together. So with the production system, again, you get the flexibility, you get the quicker lead time, flexible design, but you can see in here, those inside that inner hole, those are really, really fine feature details. So that's something that, really needs to get, metal injection molded and properly toleranced. With this, with the production system, they're able to produce this part, meet the requirements at a $3 part cost. So far, meeting or exceeding the costs, the cost targets that they're looking for this part, being able to print on the production system. And again, this is we're talking about the scale here that really supports mass manufacturing. We're talking 1 million of these parts per year. So one of these can go in every car that's coming off their assembly line. Another one here, just to give an example, where we kind of combine the geometric complex or freedom of 3D printing with the production system's sort of part cost consideration. So one of the, a lot of the parts we've seen today are things that can be produced another way that are actually cost effective to produce via 3D printing. This is something that really can't be produced another way because of this internal lattice structure. And what that really allows for this gear is this gear to be lightweighted. When you're talking about, efficiency in cars, especially with electric vehicles, lightweighting components is huge. It adds to range. It adds to, the performance of the vehicle. All these kind of considerations, are why a lot of these cars are being tried, attempting to be made as light as possible. So this is a really, kind of one of those things that gets unlocked with the metal 3D printing, and can get unlocked at scale with the production system. So this is a gear, $13 cost per part, totally within the range of cost targets on this part, and you can produce 250,000 of these per year with the production system. So really, not just cost effective, but actually a better design that has, again, these trickle down effects throughout the process of not only is it more cost effective, it's also better design that helps the range, that helps their efficiency, and all of these other things down the process. And this is actually the same fuel swirler, but you can see here on the shop system, the full build box of those packed with 641 of those parts. So the last thing I'll talk about here is this sort of digital warehouse supply chain reengineering aspect. We've got plenty of interesting topics here, but really, today, what you're looking at is a small number of big factories shipping parts all over the world, right? Especially in the automotive industry, cars are going all over the world, parts are going all over the world to factories. So really, this extends the time that it takes to produce anything by this 3 to 6 months to get parts around. What you're able to do with additive is sort of this age of the digital warehouse, right? You don't need to have centralized production in a certain spot, because no longer do you need specific machinery or the tooling in a certain spot in order to produce these parts. You can put a printer wherever it needs to be. That also allows you to minimize the shipping and warehousing costs and eliminate tariffs on these parts if you have these machines distributed around globally. So kind of the future of what you look for of this high volume manufacturing is every plant around the world can have their own machinery in-house that allows them to just take a file and print that part. That really, kind of changes the paradigm on, how we think about producing parts, how we think about procuring parts, and really introduces a bunch of new opportunities and flexibility and time to market for a lot of these. All right, so I know I've kept everybody a little bit long, and I apologize for that. but we are looking at, would love to take a look at some of your parts and sort of better understand what's next for you. So if you'd like, we'd love to, or we'll be reaching out after this. Our team would love to have a one-on-one meeting and take a look at some of your parts, see if they're interesting for metal 3D printing, and sort of get a part assessment, show you some parts and see which one, if any of our systems might be a fit for you. So with that, I think it seems like we've had a few questions come in. I'm sure plenty have been answered along the way. Anything in particular to still touch on, Ethan, or?
Can you briefly touch on the availability of aluminum? A couple people were asking about that.
Yeah, so aluminum is one of our materials for the production system that is under development today. It's something that is not traditionally a easy material to put through this process because the sintering step is very tricky with it. So with that, aluminum is under development. We've made some really exciting developments on that and been able to sinter some of those materials. So it's something that right now we're just trying to figure out the parameters, figure out the specs on how we are able to best print that in order to meet those standards that we talked about, those MPIF, those ASTM standards. That's kind of the gating factor for a lot of these new materials. Anything that is metal injection moldable is printable, but making sure that all the parameters are set right and all that kind of stuff, so the parts that actually come out are correct. That's what we have to spend the time doing. So I don't have a specific timeline on that, but it is actively under development, and it looks promising from a development standpoint.
And then can you briefly just touch on tolerances?
Yeah, so tolerances depends a little bit on the system, but generally speaking, tolerances are going to be about what you would get from a good casting. So, generally when you're thinking about this, tolerances, metallurgical properties, all that kind of stuff, if you compare it to a casting, printed parts would be a little bit better than that. But that's kind of the ballpark that we're working in. So what that really realistically means is that we're within like a 1% to 3%-ish tolerance. Definitely depends on plenty of different things on what the feature is, how it's printed, all that kind of stuff. So that's typically the range we're looking at. In addition, all of the machines have custom tailorable software. So if you notice that a part is always a % off in one direction, you can then actually scale that down a little bit when you're printing, so you can optimize those parts. And then what's nice about this systems is, especially with the binder jet systems, the repeatability, once you have that made, once you have those settings set up, those repeatability is really, really good. So you're able to, once you have your part that, your settings that work, you're able to reproduce that part at the scale that we're talking about.
I think that's pretty good. We can follow up with a few people via email if they want to shoot us over a note if we didn't get to.
Absolutely, yeah. So yeah, we'll be following up. Keep an eye on your email, and you can always hit us up on our website if you have more questions before then. Thanks everybody for joining us, and we will hopefully talk to you soon.